Okay, so hello everyone. Thank you for joining us today. So my name is Prakash, a senior cloud architect at Accenture Japan, and I'm here with my friend Marco, a senior software engineer from Red Hat.
Hey guys.
So, yeah, we'll be focusing. Thank you.
Thank you.
Yeah, so we're excited to show you guys what we're going to present today. So we'll focus on how we're going to make Kubernetes more sustainable by watching its power usage using an open source tool called Kepler. And as part of the session, we are going to integrate the Kepler with MCP and show you how it works at the end. So yeah, let's get started. Here's a quick roadmap of what we'll cover today. We'll first start with the carbon emissions in the cloud context, then what is Kepler and how Kepler works, just the basic stuff. Then once we get the numbers from the Kepler, it doesn't fulfill what we need. So we need some kind of context that needs to be added to those numbers. So we'll focus on that one, and we'll see how MCP builds that gap, bridges that gap. So at the end, we'll have an interesting demo and quick takeaways. So I'll be focusing on the boring theoretical part, and Marco will be focusing on the interesting demo part. So, yep. What are carbon emissions in cloud context first? Let's talk about that. So we often think of cloud as this weightless, almost invisible thing in carbon context, but in reality, it has very real carbon footprint. So if you see here, the data center and cloud operations, it contributes around 2.5 to 3.7% of global greenhouse gas emissions. And if you compare it with the aviation industry, it is on par with that. So even aviation industry is around 2.5%. So basically, when we try to deploy app in the cloud, it causes same pollution as airplanes flying people around the world. So can you even think of the comparison between that? And especially with the recent surge of the Gen AI, this usage and these emissions in the global greenhouse gases is going to increase for cloud and data center operations. So as a developer, when I try to deploy my application in AWS or my Kubernetes cluster, I don't actually focus on the electricity that is being consumed by the servers or the networking or storage, etc. So from my perspective, I generally see what apps which I deploy. So we need some kind of software, we need some kind of tool that can actually measure what energy or what power that's going to be consumed by my app or container of our workloads. So we'll be looking for that one. So that is where our friend Kepler comes into picture. So how many of you guys heard about Kepler? And how many of you guys have used it? Not many. Okay. So as we know, Kepler just stands for Kubernetes-based efficient power level exporter, right? So that's the full form of it. And initially, it was developed by both the Red Hat and IBM. Later, it was donated to CNCF project. And we'll see how Kepler works first. So as we know, Kepler is a monitoring tool, right? So it monitors all of the nodes in our Kubernetes cluster. So in the name itself, we have Kubernetes, right? So it tries to monitor the Kubernetes cluster. So if it needs to monitor that Kubernetes cluster, it needs to be present in all of the nodes inside the cluster. So we need to deploy in some way that it monitors all of the nodes. So we try to deploy the Kepler as a daemon sets first. So once it is deployed as a daemon sets, it has access to hardware level metrics. So it tries to focus on those metrics and tries to get that information. So if you see the architecture here, in the beginning, at the top, we have Kepler container. It is deployed as a daemon set in our cluster. And inside our container, we have a config YAML file. We'll try to mention what frequency it needs to monitor and at what mount point it needs to monitor. Like this information which will be mentioned inside the config YAML file. And that will be kept inside the Kepler. And so in the beginning, as I said, the focus will be monitoring and focusing on the sustainability goals, right, for the Kubernetes part. So Kepler, it needs to get the energy usage somehow from some point, and it needs to attribute that energy usage to the workloads. So for that reason, we'll be focusing on two different mount points for the Kepler. One is /sys and the other one is /proc. So basically, Kepler tries to get the energy usage metrics. So how it gets the information, we'll focus on the later part. But for now, Kepler somehow gets the information of the energy usage from /sys. And from /proc, we have all of the process which is being running inside my cluster. And we know what is the CPU time of that /proc. So basically, we have /sys, which has for energy usage, and we have /proc, which attributes for the process which are using the CPU. And Kepler takes both of this information, and it tries to do some math in the background, and it attributes what is the energy usage based on that to the process. So how does Kepler get this information from /sys? So basically, let's assume that the server which I'm using is or has Intel RAPL, and basically what it does is the Intel RAPL has inbuilt mechanism where inside the silicon it can measure the energy counter itself. So we don't need any kind of external modules that needs linkage. So it's actually faster to measure those metrics. So once we get that information, the Intel RAPL tries to store it inside the MSRs. And once it is stored inside the MSR, we have Intel RAPL drivers present inside the Linux kernel. So that Linux kernel get those measurements, and it tries to put it inside the sysfs mount point, sysfs storage. And now what happens is we say that you need to store that information inside /sys and /class and /powercap, which you see there. Yeah, so basically the information which is being gathered by Intel RAPL is put inside MSR, and MSR get that information through drivers, and the kernel take that information and put it inside the /sys. So basically Kepler, it tries to get that information through /sys. And basically, one more thing to note is that we are just reading the information. We are not writing any kind of information there. So it's basically a read-only. We don't need any kind of elevated privileges here for /sys. So simple, right? Next, as we see here, we get the information. We put the configuration file, we get the information from /sys, /proc. So we need to get that information somehow, and we need to visualize that, right? For that, we have Prometheus. Basically, we'll set up it in somehow that Prometheus scrapes this information from Kepler container, and through Grafana, we can monitor that. So that is how this whole data flow in Kepler works in general. And if we go down here, so as I said, /sys is getting the energy information, and /proc, as I said, we need to get the process level CPU watch time. So Kepler does that as well through /proc. And here as well, we just need read-only. We don't need any kind of write. So the host path for this daemon sets is this, and it's a read-only. So how does Kepler knows which process belongs to which container? So it watches that via C groups. So it understands that this process belongs to this specific containers. And how do we know that this specific container belongs to this specific pod? It does it through K8's API, Kubernetes API. So it has all of this information set up inside the Kepler. So it has a clean matrix that this process belongs to this pod, and this container and this container belongs to this pod. So these all kind of clean information is there. We have energy and we have CPU time, so it can basically assign all of that, and behind the math, based on the math, it can assign that. Next, we have something called as proportional energy split. So let's say I have my node, and my node has been assigned 40 watts. And let's say the node has only 25% of its usage which is running. So 25% of the 40 watts is 10 watts, right? And in my cluster, in my node, let's say only one process is being utilized. So basically, 10% of CPU percent, let's say it is utilizing. So 10% of the 10 watts is, 25% of the 10 watts is like 2.5 watts. So let's say it's a clean, right? So we have node and we have pod inside it. So node has 10 watts utilization, and part of that 25% is busy through the CPU. So 2.5 watts utilization. So that kind of math implementation is being put inside Kepler. So it can understand that it needs to assign this energy proportionally based on the /sys and /proc. And as I said, it's minimal overhead. So all of these both host paths are put as a read-only. We don't need any kind of elevated privileges. So no black magic kernel tricks here, just /sys/proc and some math. But whatever the information which we get from Kepler is just numbers, right? So let's say pod A is using 10 watts, but how do we know that 10 watts is bad or good? That's the information which we need, right? So that's the question as part of this session. So we need to understand that first. So yeah, numbers alone aren't good enough for us. We can't actually tell if the 50 watts which has been assigned for the pod is good or bad. So yeah, so we need some kind of context for that numbers. So what is that context? So that context has to be assigned automatically. We need to get that context automatically. So that context could be like, we need some kind of regulations. We need some kind of SLA limits, like those things, like the targets and policies, and carbon factors, like kilowatt hours in Seoul is not equal to kilowatt hours emissions in Stockholm, right? It's different. So that needs to be, that context needs to be put to the Kepler. So it needs to understand that, because right now, as of now, it's just numbers and baseline and benchmarks. So the usage right now in this week is 40 watts. What about the previous week? So is it good or bad compared to that? So that kind of comparison is also needed, but that is also not present as of now. And we need some kind of action hooks as well. So once we get that information, what are the suggestions that it's going to give? So do we need to scale? Do we need to tune the limits, like increase the vCPU, RAM, or do we need to reschedule our pod? Like this kind of information is not being visible through the Grafana dashboards, which we showed in the previous architecture. So that's what's missing. So if we see the bridge, let's say we need some kind of information like which pod exceeds our CO2 budget in AP Northeast 2 right now. So this kind of information is not present to the Grafana dashboard. So we need these kind of questions inside, and we need the answers that needs to be given. So how are we going to implement it? That's the question. That's where MCP comes in. So how many of you guys know about MCP here? And you guys worked on it? Perfect. So as we know, MCP stands for Model Context Protocol. It's basically an open standard. So you can say it's like a USB-C for data and AI. We can basically mount tools, external tools, or AI model, and we can make it queryable so that it can understand the context behind it. So how are we going to implement the Kepler and MCP? That's the question. So basically that part, as part of the demo, Marco will concentrate on that. Then to make it concrete, think of a real-world question. So which pod exceeds 0.1 kilos of CO2 emissions today, as per the EU regulations? So that kind of context is not present. So for this, if I need to do it manually, I'll try to get the information from Kepler. I'll try to get the information, like the context which I got previously, SLA limits, regulations, and I need to put it in a spreadsheet, and I need to do all of this stuff manually. As of now, there's no solution for this part. So that's where our presentation comes into picture. What we did here is we are basically trying to integrate the Kepler with the MCP, so it does not only give the numbers, but also gives it with the context, which answers the question, which pod exceeds 0.1 kilo to 0.1 kilos CO2 today as per EU regulations. So after integrating with MCP, it gives us answer like pod A exceed the 0.1 kilos of CO2 as per EU regulations today. Like this kind of information is present, not present as of now. So yeah, that is what we need, and that is what will be shown by Marco. Over to you.
Thank you, Prakash. Hey guys, my name is Marco González, and today I will be in charge of showing you the demo for this presentation. As many of our sessions before, I want to, before showing the demo, present you the goal of the demo. What we're trying to aim with this demonstration. This is a real-time dialogue with your workload energy profile. And the goal of the demo is to support Korea Carbon Neutrality Act that was signed in September 2021. That act says that by 2050, Korea should achieve the net zero carbon emission, which is a major goal worldwide. Over 14 countries are trying to achieve this value, so Korea is one of them. In order to achieve this, there are milestones. By 2030, they should cut down over 40% carbon emissions. For this demo, I just will use two KPIs, which stand for indicators. The main KPI, the first one, is the PUE, that stands for power usage effectiveness. It shows the data center power usage and how the total facility energy divided by the IT equipment energy should follow one value, which should be below 1.4. Please remember this value because I will use in the demonstration. The second KPI is the Korean grid carbon intensity. This is a very broad KPI, but I wanted to focus on this demonstration because the value used, it refers to the CO2 or carbon dioxide equivalent per kilowatts hour, which is basically, in simple words, what is the carbon emission when you use a server. Those two KPIs will be used in the demonstration. So I wanted to show you guys that for those who don't have a lab environment at home, you can deploy this demo. I use AWS Cloud Services, just personal preference, to deploy this solution. It's one C5 bare metal. Kepler uses right now ODAT 11.2 version, which is applied for bare metal servers. Deploying this T5 metal as a unique server, on top of it, I install the lightweight Kubernetes K3s, and on top of it, I have Kepler as a pod, and along with the MCP that I will explain later. Besides this, having all solutions in cloud gave me the chance to fully automate it. So I will show you how you can just run scripts to deploy all this demo by yourselves. Now, let me explain you how I divided this demo in layers. The layer 0, the main layer, is the AWS C5 bare metal. That's going to be the raw data. As Prakash explained before, interRPL will show the information, the counters in microjoules about the workloads running information. Now it's a layer 1, Kepler monitoring. As we mentioned before, Kepler will collect this information. It will collect the dynamic live power energy counters. It will use the 6-class power cap for that, and it will use a concept we define as wrap zones. So it will have zone 1 and 2 for these CPU, and 3 or 4 for memories. That's how Kepler works. The output is the metrics that we can use. Now that output will be taken by the MCP server, and for that I will use MCP tools. There is one talk, same times, we'll explain about fast MCP. It's a shame that we have same time because I was hoping to use that session to explain the versatility of fast MCP. I use fast MCP 2.0, which is one of the most common and easy frameworks to deploy an MCP server. Why is that? Because simply use MCP tools or Python decorators, I can define multiple use cases, multiple scenarios where I can work with my MCP servers. Of course, MCP server can talk with an API agent, with an endpoint as well. But for this demo, because I'm using fixed values like a PUE and the local government regulations, there will be just static values. So MCP tools allow me to run many queries and give me compliance assessments, recommendations, and in the JSON RPC responses. Last is a layer 3 client. I want to make this demo more user-friendly. And what is the most common way to do it? It's a chatbot, right? Cloud Desktop has this feature to install a remote MCP server. So using that option, I can have natural language interfaces and user-friendly discussions with my MCP servers, which will get information from the Kepler itself. So this MCP compliance tool that I talk, for this demo, I talk about 8 MCP workflows or MCP tools. You can define as many as you want, as many as your use case involves. In this case, I start with the easy ones, list top power consumers, identify power hotspots, up to the most complex ones, which is give me recommendations. What should I do if I have a workload that demands more some actions? And I just quickly wanted to explain what the fast MCP feature is. To have this solution is based on a Python decorator, which is a special function that wraps another function. In other words, a function inside another function that I call. For instance, if I want to define a list of the workloads that has a high compliance or not compliant with Korean regulations, I'll first need to list all the workloads, all the pods. Then for each pod, I need to run a query asking what is the workload, what is the CPU and memory power consumption, and then I make the report. That's made easily with decorators and with fast MCP. Okay, now let me go to the demonstration. Hopefully you can see the image here. And okay, so first, as I mentioned, I will use the AWS server. I will log in into the server. In this case, the Ubuntu one. Let me show you here. Yeah, once I log in, I need to start here. Why? Because as we explained before, the main component is the Intel RAPL module, and AWS demands some workaround. It's not that easy. So Linux kernel that AWS service uses do not expose the Intel RAPL information. So there is a way to patch it. And by the way, all this demo is in my GitHub repo, so you will have access to it, and you will just check the information. But after I installed the modules, the Linux kernel modules, to have the Intel RAPL, I was able to collect the information as we explained before. So I just verify this. We have the Intel RAPL common and MSR available, which is good for our demonstration. Yep, so you can see here, this is the RAPL zone that I was talking about. I have 0, 0, 0, 1, 1, 0, and for each RAPL zone, you will get the energy in microjoules information, which is the node or the zone consumption that's happening. Okay, I verified I have the source information. I verified that I can collect the energy in microjoules. Let's move on. This is the K3S server running our cluster for this demo. So I want to show you the Kepler system. The Kepler system can be as simple as a daemon set which support at the end and expose with services. I use this service to collect information as Prometheus and therefore use cases for Grafana. And I'm collecting the URL to get a metrics. And this is what Kepler does. Simple as it. It's giving me the information in watts, in this case, about the CPU. And the CPU is called zone package. And the zone DRAM is for the memory. That's information you get with Kepler. Nothing new. You already know about this. And you want to fetch port information, you can do that. Same. So I will move on to the actual MCP server. So this is the MCP installation. For that, I use an image to build and to deploy the MCP, so it can be deployed on top of the K3S. This is for demo purposes. For production ones, I recommend to use a dedicated server because the MCP can get really complex. So the Kepler is one initialized. It will load the 8 MCP tools, and it's ready to go. It's ready to be used and collected. Now, if I don't have any user interface and just rely on Kubernetes kubectl commands, I need to run a command like I show in the screen to collect the node, CPU, and DRAM energy consumption. Well, that's one option, of course, and I can go with the actual pod information, same. I am listing the pod, CPU, and DRAM consumption in the total one. That's how it will work in a very CLI black screen way, but the demo wants to show that we can also include some user-friendly integration. For instance, this is the information for a non-compliant carbon-heavy batch processor that I defined for this demo. As you can see, this is using CLI, I can get information. But let's use the actual MCP client integration. So I will go to this one. Let's see. Okay. So this is the prompt for the MCP client. Before that, I need to set up from the MCP client the configuration for the MCP server. Once it's verified and configured, I can ask the question for list all the workloads in the demo workload namespace and show me the consumption in watts. Include compliance status with Korean standards. So as I mentioned before, I try to verify the compliance status. And if I want to get more, let's say, detail or want to be more specific, I can ask for detailed information. How it works is every time that I run a query, it will list the compliance, use this decorator function, and will list, access, and evaluate each node. This is how it works. This I can see. Why I see this in green color? Because although the PUE is for the data center and many of the pods doesn't comply, if you have an idle pod or a pod not working, it of course doesn't have any carbon emission, and it's of course compliant at this point. This is just a thing we want to show you guys. You can actually ask questions relevant to the workloads, get recommendation, and the very last one before the times. We can also ask, give me or get migration recommendation for this carbon-heavy batch processor, the one that I showed you before. So it's recommended because we deploy in AWS. I can actually ask the MCP client to give me recommendation. So it's recommending me to Seoul region. It has a very strict PUE and KPIs. So you can migrate your workload to another region. One of these is Stockholm in Europe North, or you can move to the Oregon in the US. So that's a feature I want to show you in the demo. Let me go back to can you please wait for the slide? So the demonstration, again, is available in the repo. You can access it. 1 hour of this C5 metal costs around $4, so you can just play with it within 1 hour. There's the QR code. You can just clone it and use it. And just takeaways. Just a couple of them, guys. The first one is Kubernetes energy enables carbon accountability. I showed you before with the demo in with information that Interrupl provides direct hardware for our energy counters in joules or watts for CPU and RAM. And that enables carbon chargeback. It enables us to interact with MCP servers, with end users to analyze, to get feedback and actions how to improve this. The second one is cloud but open source is a production level solution. I'll show you in this small demo how I deploy an C5 server and how I deploy on top of it all the Kepler and MCP. So you can take this as a reference and just apply a standard like the Korean and have a use case ready to release. Finally, I want to invite you to the Kepler community. We have bi-weekly calls in English, and we are more than welcome to having you guys, developers, researchers, to work on this. This is a GitHub repo, this Slack, and more than welcome. We really want you to be part of this open source project. It's a sandbox, by the way, so more than welcome to have you on board. And with that, that will be all. Thank you so much for your time, and I hope you enjoy the rest of the day. Thank you.